Hello. Uh, in the previous lecture, we have finished a few of the important topics concerning complex numbers, and we've been able to establish a little bit of understanding about complex numbers and different other properties of argument, modulus, and from today we're going to start more on the analysis side. Okay, so it's not that key complex numbers are completely over. We would do some questions every now and then in the middle of other lectures also, so that's not a problem. So that will keep continuing, but in order to keep the continuity intact and in order to move forward, let us today start with topology of complex plane. Okay, and please I'm mentioning this is an important topic, although I may teach you for one day or something, but you will have to uh, remember the concepts discussed in this particular lecture, and we are going to use it time and again throughout the course. So this is very important. So please don't skip it, or please don't uh, listen to this, or please don't don't, you have to be very attentive for this lecture. That is what I mean to say. Okay, so without wasting the time, let us start with the topology of the complex plane. Okay, so again, as I mentioned, you can follow any of the textbooks. Most of the textbooks would have this topology section, and still the most important thing is that you have to keep remembering the things. That is the important thing. Okay, so in this particular lecture, we're going to start with this. We are going to start with the. We are going to start with the. So we are going to discuss the topological properties. So our aim is to discuss the topological properties of the complex numbers, or topological properties of the complex plane. Okay, complex plane. So we have to start with the topological properties of the complex plane. Let us first define something called as the metric space. So I'm not going to going in detail about metric space, but with regards to at least definition, you should be acquainted, because most often I'm going to use this terminology time and again. So let us first discuss what is metric. So as the word indicate, metric means what? Metric means distance. Metric means what? Metric means distance. So if x be any set, if x be any set, then the function, then the function d from x to x, and let's say to in general, let me keep it to r, because ultimately r is going to uh, determine the distance. So let d be a function from x cross x to r. This particular x is called metric, is called metric or a distance function, or a distance function if it satisfies the following property. If it satisfies the following property. What all property does it satisfy, or conditions you can say on x? Okay, so okay, so if x be any set, then the function d from x cross x to r is called a metric or a distance function if it satisfies the following property. Property number one is the distance between the 2 points, let's say a comma b, following property on, yeah, for a and b, and in fact c in x. So what are all properties? The first property is that the distance should be always greater than equal to 0. Second property is the distance of AB, if it is equal to 0, then A has to be equal to what? It should imply that A must be equal to B. Third property is that symmetricity, that distance of AB should be equals to distance of BA. And the fourth property is that distance of A to C is always less than equal to distance from A to B plus distance from B to C. All these properties must remain intact, only then we can define something called as a distance function, and that distance function in general is otherwise also called as metric function. So let x be any set, then the function dx cross x to r is called as a metric or a distance function if it satisfies the following property for a, b, c in x, that is dA comma b should be greater than or equal to 0. dA comma b is equal to 0 implies a equal to b if dAb is equal to dBA and dAc is less than or equal to dAb plus dBc. If following properties are satisfied, we call that we have defined something called as a metric function. We have defined something called as the metric function. Now, if I use this D along with this set X, then that particular set is called as, that particular space is called as a metric space. So what is a metric space? Metric space is nothing but it is the set together with the set together with this distance D. Okay, with, you can say, metric. That is, if I will write in this fashion, x comma d. This is called as, this particular space in general we use most times the shorthand. That is simply x only we do write. We don't write x comma d. Is called as the, is called as the metric space. Is called as the metric space. So in particular, we are discussing what? We are discussing complex numbers. So let us define the distance in complex numbers. So how the distance is defined? By modulus. So let us take d in r. Sorry, d for. Let us define a metric function on C cross C. So how do we define generally distance? So if z and z dash are two complex number, then the distance is given by the modulus z minus z bar. Okay. And here I refer to the Euclidean distance. Euclidean distance, you know, Euclidean distance means what? So if these two are the numbers, and let's say z is x comma y and z dash is x dash y dash, then this distance is given by x minus x dash whole square plus y minus y dash whole square. So this is how you define the distance. This is called as a Euclidean distance. Okay, so you'll find whenever you're going to study metric spaces in detail, there are different other distances possible. So let's say there is something called as a maximum metric, then there is something called as a taxi cab metric. So there are different other ways of defining the distance, but right now we'll focus our attention to find to the Euclidean distance, that is distance expressed in this particular format. So since we are studying complex numbers, so I have written d c cross c to r, where d is given by z comma z dash is nothing but modulus of z minus z dash. Okay, and remember this particular distance has also the same properties. So this forms a metric space. So see how if you take the distance of any complex number from other complex number, let's say z dash, it is always greater than or equal to 0, point number 1. Second property, if I take z minus z dash modulus equal to 0, it does imply that z has to be equal to what? It does imply that z has to be equal to what? Z dash. Third property, we know that if z minus z dash modulus I write, or I write z dash minus z, symmetricity is intact. So there is a sense of symmetry here. And triangles inequality we have already discussed in set of complex numbers. So z minus w mod is always less than z minus z dash plus z dash minus, so transitivity. So this is also intact, where z, z dash, and w all belong to set of complex numbers. And here this, it implies what? It implies what? It implies that C forms a metric space. C forms a metric space with respect to D, where D is the Euclidean distance. So with respect to Euclidean metric or Euclidean distance, D, Z minus Z dash given by modulus of Z minus Z dash. And you know what is modulus of Z minus Z dash? That is root over x minus x dash whole square plus y minus y dash whole square. So this is clear to you, I hope. In fact, you can also extend this entire thing for, we can also write this for the real number. So we can actually use x is equal to r also. And then we can write that this is called as a real metric space in that particular scenario, so where dx comma x dash is nothing, but it is equals to modulus of x minus x dash. So we can also say that r comma d also forms as is also a metric space. So we are going to keep our attention to most often to this thing. Uh, Okay, we'll focus. So from here itself, it is clear that if you already know that this R is contained in C, okay, R is contained in the C. So always remember that if Y is a subset of X, is a proper subset of X, and X comma D forms a metric space. X comma D is a metric space. So is the space Y comma D. So is Y comma D. Okay, so if Y is contained in X, let's say we proved this for C, C forms a metric space and R is a proper subset of C. So basically, R comma D also forms a metric space. So basically, if Y is contained in X and if X comma D is a metric space, so is the restriction. So is the restriction Y comma D. So if I restrict the space to one of its subset, then this also is a uh, metric space, I think. I hope it is clear till now. So we have not written much. We have just started it. Metric in general, understand if people have joined right now. Metric only means distance. So just don't make a big fuss about it. Metric simply means distance. Following these properties, that distance function should be greater than equal to 0. Distance AB equal to 0 means A should be equal to B. There must be a symmetry, that is dA comma B. The distance function itself. Right now, the distance function we are taking is the Euclidean function. Okay. So dA comma B should be equal to dB comma A, and dA comma C should be less than equal to dA comma B plus dB comma C. So this is a little bit about metric space. We are not studying metric space, just that we are going to use the definition every now and then. So therefore, it's advisable that you remember the definition for metric space. Okay. So once you know the definition to the metric space, now I can use it quite comfortably every now and then. So you have to remember it. I mean, it's an important topic in mathematics, and one needs to give a lot attention to this particular topic. But that remains a topic of discussion for another lecture. Right now, just remember these properties, and these properties for the distance d. And when the set x I'm talking about, let's say c. So when it is equipped with this metric function, then it is called as a metric space. And right now, for the today's discussion and for most of the discussion, we would be discussing it with respect to the Euclidean metric only. So don't worry, Euclidean metric you already know from your standard 10th also. So distance function, you know, this is how we define the distances. Okay, in the Euclidean way. Okay. Now see, just give me a minute. Okay, so this is one thing. Now see what I have to write. Uh, the first thing that we will use most often is called as an open ball, or generally whenever we have to define a neighborhood, whenever we have to define a neighborhood, what do? We define something called as open ball. So let us first define something called as open ball. Open ball, at times you'll find the same way written as open disk also. Okay. So in order to define a neighborhood, we use quite often something called as open ball or open disk. So in Euclidean metric space. We've already know that the C with respect to Euclidean norm forms a metric space. So in Euclidean metric C, comma D, an open ball is given by an open ball centered around Z naught is given by. So basically, most often you'll find books using this notation. I will use this notation and I will also use possibly this notation. So if I'm writing B, Z comma epsilon, it implies I'm talking of all those complex numbers belongs to C such that Z minus Z naught modulus is less than epsilon. So this is called as the open ball or open disk. And what does it represent? It represents a small radius. Small means whatever is the epsilon. So usually we take epsilon very small. So this particular area, not including the boundary, but this particular area, this particular whatever shaded region I'm drawing, this happens to be mod z minus z naught less than epsilon. So this is an open ball. This represents an open ball centered at z naught with a radius epsilon. So this is how you define an open ball. Okay, and this open ball, what does it? Why do we need to define it? It also defines the neighborhood, an epsilon neighborhood of. It also defines an epsilon neighborhood of the point z naught. Okay, so basically, whenever I'm going to talk about neighborhood of z naught, I would mean an open ball containing the point z naught and with certain radius. Let's say here we have defined epsilon. So this is how we define an epsilon neighborhood of z naught. So whenever I'm saying, let us define an epsilon neighborhood of z naught, I would mean an open ball around z naught with a radius epsilon, and this is how we are going to visualize it. Is that fine? I hope it is clear till now. Okay, so this is how you define an open ball or open disk. All these things you need to remember. I mean, this is definitions. Okay, so one cannot argue here. So this is how it is. Okay, it is fine till now. Okay. Otherwise, also you see, what does it mean? It means that we are finding all those points with respect to z naught whose distance from z naught is less than epsilon. So it also signifies the distance of all those z belongs to C from z naught such that this distance is less than distance, that is z minus z naught is less than epsilon. So basically we are finding all those complex numbers z whose distance if we take from z naught turns out to be less than epsilon. So and this will eventually form a disk. This will, if this particular, if you just take x is equal to x comma y and x naught as sorry z naught as x naught comma y naught, you'll find that this particular disk, this is an open disk. Please remember, in the open disk will not have the boundary points. Okay, we'll not have the boundary points. So all these points, I mean, there are points in between also. Just making it so that you can get to understand that all these points within, okay, there would be all these points within. These points follow the definition mod z minus z naught, mod z minus z naught less than epsilon, or we can say this is nothing but in notation this way or this way. Whatever suits you, you can use the notation. Most often I'm going to use this. Most books use this kind of notation, so I'm using this also so that you don't get confused. Okay, so this is one thing. In fact, while defining the limit, so when limit is necessary, only when a function is not defined at a point. Let's say I'm saying find the limit x tends to 0 sine x upon x, or let's say I'm saying find the limit z tends to 0, and we'll define what sine z means and all those things. But right now, just think about it. If I'm saying that find the limit z tends to 0 sine z upon z, and let's say if I say it is equal to 1, it, you see, when is there a need to define a limit? Only if the function is not defined at that point. See, if I place 0 here, so it will give me an indeterminate form. So understand that limits, to define a limit, one needs to define something called as a deleted neighborhood, because at possibly wherever you're finding that limit, your function may not be defined. So one needs to define something called as a deleted neighborhood of a number z naught. Okay. If I want to delete this z naught, what I have to do? I have here, if you see, mod z minus z naught is less than epsilon, so it covers all. Now, if I add an additional thing, that if I take this distance to be greater than 0 and less than epsilon, then this defines something called as the deleted neighborhood of z naught. Because if I'm taking distance greater than 0, it implies that z cannot be z naught at in this particular region. So how do you define deleted neighborhood? You define deleted neighborhood by this: z minus z naught modulus should be greater than 0. It implies what? Understand the mathematics behind it also. This particular scenario means you're trying to find the complex numbers whose distance from z naught is greater than 0. So it cannot be 0. Greater than 0 means what? It has to be greater than z naught. So you're finding all those complex numbers who are greater than z naught, whose distance is greater than whose distance from z naught is greater than 0 but less than epsilon. So it will define an open disk except the point z naught. So at times you also find something called as punctured disk at z naught. This is also a little bit of most books use punctured disk at z naught means uh, there is a disk which is centered at z naught but does not contain z. So this is how you define the deleted neighborhood. You can also write it as in short. In short, you can write this way. Or you can write this. Whichever way suits you, you can write this one. So this is how you define the deleted neighborhood of z naught or punctured disk at z naught. Is that fine? Till now, everything is fine, I hope. Okay, so these are just terminologies. You need to remember them. Okay. In particular, we may use something called as a unit disk. So unit disk means what? In that particular scenario, your radius would be equal to simply 1. So if I'm saying a unit disk uh, centered at, let's say, 0, centered at origin, how would you define it? Let us first define, in general, a disk of radius r. So centered at origin means, it means what? It means you are trying to find all those complex numbers such that modulus of z should be less than r. And in particular, if we take r equal to 1, then we are talking of something called as a unit disk. So unit disk centered at origin would be simply mod z minus 1. So basically, if I'm talking of unit disk, it implies I'm talking of something called as I'm talking of all those complex numbers such that modulus of z should be less than 1. Why modulus of z? Because in this particular case, we have chosen z naught to be equal to 0, 0. So clearly, this is how you define the unit is centered at origin. Is that clear till now? Now something called as open set. अरे कोई बोल क्यों नहीं रहा है? बोल तो रही हूँ सर. Only है ना? Clear है ना? Everything is clear, okay? हाँ. I think my अच्छा मेरी voice आती रही. चलो ठीक है. Okay. Now let us discuss something called as open set. All these things you might have done in your real analysis part also, but just for the sake of revision, you should be, and plus the sense of writing it, because see, complex numbers, there is a, you'll have to, so therefore I'm doing it so that at least writing part you can do quite easily. In fact, the books also, probably there would be books where you may not find all these definitions written at one place. So they would use directly. So one has to understand all these things. Possibly open any book of complex analysis. Konosami will have this kind of topic, don't worry. But let's say any other book, they will use directly open set and close set. So therefore, I'm mentioning it here. Okay. So a subset S of a complex number is called as an open set. Is called an open set in C. देखो सेट ओपन कब कहलाता है? When let's say this is your set S. Okay, at any point if you take any point, then there must exist a neighborhood of this point contained in this set itself. So if I'm, and this point is called as interior point in that scenario, and an open set will have all the points, all those points whose neighborhood, some neighborhood I'm saying, whose some neighborhood is contained in that set itself. That set is called as an open set. Is that clear?
Yes, sir.
Okay. So, so it implies what? Let's say a subset S is called as an open set in C if for every means what? Every number that lies in this particular set S, for every Z naught belongs to it, there must exist some del greater than 0 such that B Z naught comma del must be contained in set S. So a set is said to be open if all the elements neighborhood of there must exist neighborhood of all these elements, and that neighborhood must be contained in that set itself. Then we say that set is an open set. Okay. So let us say, for an example, interior of a circle. Interior of a circle. Interior of circle, let's say unit circle. This is an open set. Okay, so each point, whatever point you choose, you must be in a position to define a neighborhood of that point which is contained in that set. If that is the case, any neighborhood, I mean, it's not necessary. There must be some neighborhood of that particular number or that particular element of the set which must be contained in that set itself. Only then we are, only then we say that that set is an open set. Okay, so if we cannot include this boundary, because if we include this boundary and if we take any point on the boundary, let's say we take any point on the boundary, now if however small epsilon we try to make, there would be some the neighborhood cannot be entirely contained in set S. So always remember, open set will not contain the boundary point. We'll see what is boundary, but it will not contain, right now just understand boundary in the sense of boundary only, will not contain the boundary points. Is that clear?
Yes,
So
sir.
what is an open set? A set is an open set if for every Z naught belongs to S, there exists some del greater than 0 such that P Z naught comma del is contained in S. Or you can also write this way, delta Z naught comma. I'm doing it just because you don't get confused with the notations. So every element of the set S must be having a neighborhood which is contained in that set itself. Only then. And this point is called as interior point. We'll discuss it lately, but this is called as the interior point. And in fact, the set of all interior point is called as an open set also. Okay. In fact, any interior of the circle, it's not even unit circle, you can take any interior of the circle. This is also an open set. In fact, your entire complex plane, the entire complex plane is also an open set. In fact, the half planes, that is the real part of Z less than alpha, and let's say imaginary part of Z greater than some alpha. And you can just, for visualization, you can keep alpha equal to 0. So what does alpha equal to 0 means? So this is your real part of Z equals to 0 means what? Real part of Z equal to 0 means what? Uh, this particular thing. Okay. So real part of Z greater than 0 means what? This particular area. So in fact, if I use alpha equal to 0, this particular region is called as a real part of Z greater than 0. Clearly, this region is an open set. If I say imaginary part of Z greater than alpha and alpha is equal to 0 here, then this will be imaginary part, not including this line. Okay, this line would be equal to, it will be equivalent to saying imaginary part equal to 0, but I'm not using it. I'm just writing imaginary part of Z greater than 0. Okay, in fact, you can write, and do remember, let's say if I'm saying complex numbers in the unit circle. So remember that this boundary doesn't come. This boundary doesn't come. Only this interior of the circle would come. Okay, so whatever I'm mentioning, this is an open set, not the boundary. So boundary won't come. So if you take any boundary point, that is, this is how we denote the boundary. this will not be in the open set because any the neighborhood containing this boundary point will not be contained in this unit circle. So boundary point do not account for the open set. Okay, so they cannot be in the open set
Yes, sir.
because no neighborhood of the point on the circumference lies completely inside the set. Okay, yeah, completely within the set. So always remember that in defining an open set, the interior of the circle would do, but interior of the circle plus the circumference of circle will not be an open set. So remember that because no neighborhood of a point, no neighborhood of point on the boundary lies entirely within the circle or within the disk. So therefore, this boundary points do not form an boundary point are not in the open set. So what they are called? They are called as they are set to form something called as the closed set. Okay, closed
Yes,
set.
sir.
Okay, so I can write that Z belongs to Z such that modulus of Z less than equal to 1 is not an open set, rather it is a closed set. And what is a closed set we'll see, but right now understand a set which is not open, this is called as the closed set. Okay, so this is a closed set. This is not an open set. Okay,
Yes, sir.
okay. So there are a few things that one needs to understand and one needs to know. Uh, Dekho, I'll write it here so that you get it. Okay. So remember that the complement of an open set. So I'll write it here. So complement of a set S, which is a subset of C, uh, we usually denote it by SC. So this is how we denote complement of set C, or at times you can also write this way. Okay. So from C, we are not seeing we are not seeing the points of S, rather other points. So basically this denotes a complement. I hope it is clear. So a set S is said to be a set S, which is a subset of C, is said to be closed if its complement is open. Okay, this is some, I'm not deriving it, but I think you must have done all these things in your real analysis class also. So if SC is open, then we say that S is closed. Okay. In fact, the most general definition for a closed disk would be all those complex numbers belongs to C such that Z minus Z naught modulus is less than equal to epsilon. So this is a definition for a closed disk centered at Z naught with a radius epsilon. And how do you denote it? You denote it by a bar written over this thing, or you can write this way. So this is how you define a closed disk. So this is how you define a closed disk centered at Z naught with the radius epsilon. Is that fine? I hope it is clear.
Yes, sir.
Okay. All these things you might have done, so I'm not focusing much on this. So let's say if I'm talking of something called as let's say something called as I consider a unit disk. So a unit disk would be what? You will have open disk. Okay, open disk, open unit disk. So this is equal to this. Okay, if you want to write a complement, if you want to write what you can say, um, a closed unit disk, then this would be this. A closed unit disk will be this. If you want to write the complement of this, so complement of this would contain all the complex number except this. So it will be mod z greater than equal to 1. And if you want to only write the boundary, then boundary will only consist of the points on the boundary. So boundary is this.
Equal to
So,
one.
okay, so all these things I'm mentioning so that you can get acquainted with this. So basically, my idea from these lectures is the acquaintance, because I know that all of these things you might have done in your real analysis also, but just for the sake of acquaintance so that you remember all those things. Okay, so we have written that the entire complex plane is open also. Also remain that entire complex plane is closed also, for that matter. And we'll see all these things because closed we have not yet defined. Okay. Um, this set, what can you say about this set? This set is also closed. Says that we did real part of z greater than 0. If I use greater than equal to 0, this is also closed. If I take imaginary part greater than equal to 0, this is also a closed set. If I use greater than 0, then it is an open set. But equal to 0 means I'm including the boundary. It implies it is closed. Why it is closed, we'll come to see. Entire complex plane is both open as well as closed. So we'll see why it is closed also. Uh, for that, one needs to define something called as a limit point. So that we'll see later on. Uh, even this, for that matter, says that z minus 4 modulus is greater than equal to mod z. So all these sets are nothing but these are closed sets. Or okay, a closed set. Is that fine? Another way of characterizing the closed set is via limit point. Is via limit point. Let us first define what is a limit point. So a limit point is such, if I'm saying that there is a limit point, let's say if I'm saying that z naught is a limit point, then every neighborhood of z naught, I'm now saying every, I'm not saying any neighborhood. Earlier when I was defining open set, I was saying that if a set is open, then there must be some neighborhood of all the points, yeah, all the elements of set S contained in set S. Now here I was saying any neighborhood. Any neighborhood means some neighborhood also would do. I mean any specific neighborhood would do. Any neighborhood would do. But the point is this: this neighborhood must be contained in the set itself. This is the condition. And this is the precise reason why the boundary points are not included, because if we take any neighborhood of boundary would contain some points which are outside. So it cannot be contained completely within the circle. Here also one has to understand whenever we are defining limit point, now any neighborhood of point z naught must contain elements other than z naught. Okay. Only then we say that that particular point z naught is a limit point. So if I'm saying that z naught is a limit point, then the neighborhood containing z naught must contain points other than z naught. Is that fine?
Yes, sir.
है And this is true for every neighborhood. Means every neighborhood of z naught. I'm writing. अच्छा एक काम करते लिख लेते पहले. Otherwise you'll get confused. A point z naught is called as the limit point. Is called as the limit point of z naught of, let's say, set S, if please remember, every neighborhood of z naught, that is delta z naught comma epsilon, or you can say whatever you like to say, p z naught comma epsilon, contains a point of S other than z naught. Okay, now this point may belong to set S or may not also belong to set S. So both of these possibilities are there. You know from your sequence also, one of the very profound example is this. You know that the limit point of this set is 0, and z naught equal to 0 is the limit point of set S, but it is not contained in set S. Okay, so it is not the guarantee that if something is limit point, then it has to be contained in the set. Okay. Is that clear till now?
Yes, sir.
Okay. Okay. So this is a little bit of open set and closed set. And okay, now the point is this up. What about this thing? So see, if we take something called as Z, if we take something like let's say an open disk, and let's say it is an open unit disk. So let us consider del, where del is equal to Z belongs to complex numbers such that mod Z less than 1. Now, what will be the set of limit points? What will be the set of limit?
यूनिट सर्कल में लाइक करने वाले सारे पॉइंट्स
Okay. Now see here, understand this thing. I'm saying just think about boundary.
लिमिट पॉइंट्स होंगे.
Yes, exactly. So these boundary points are also limit points. So basically, if we take any of the points, let's say this point I'm saying, then any neighborhood, if I make, it contains some points of S other than this point. Okay. So what is the definition? Z naught is said to be the limit point if every neighborhood of Z naught contains a limit point of set S. Z naught is called as a limit point of set S if every neighborhood of this Z naught contains the points of S other than Z naught. So clearly, even the boundary points are also the limit points. So here, even these points, that is mod Z equal to 1, are also limit points. Remember, these are not contained in this del. But if you want to write the set of the limit points, these would be simply Z belongs to C such that modulus of Z is less than equal to 1. Is that clear?
Yes, sir.
And these points are not contained in the not
That
mod Z equal to 1. These points are not contained in the set del, but still they are the limit points. So it is not necessary that limit points will always be contained in the set. It may be possible that limit points might not be contained in that particular set. So one of the example was S equal to 1 upon n. Another example I gave you this way. So all those things you have to remember. All these things you have to remember. Okay. Now there are some trivialities. You think about them. I'm not going to focus much attention here. So the set of entire complex plane is both open and closed. I think this you can do on your own. If you are not able to do, then ask me. I'll let you know. Set of this entire complex plane is both open and closed. Now it is not possible. It is not always that every set is open and every set is closed only. There may be possibility that a set neither be open nor closed. For example, if I make a disk this way less than equal to 1, and then I do this way.
correct.
So now this is neither open nor closed.
Yes, sir.
Neither open nor closed.
Yes, sir.
Okay, so all these things you have to remember. I think you can do it on your own. So I'm not focusing much over all these things. Okay, now remember, a set is said to be closed if and only if it contains all the limit points. So a set is said to be closed. Initially, we saw that a set which is not open is closed, but more proper definition would be a set is closed if and only if set contains all its limit points.
Limit point.
All of its limit points. Then we say that that set is closed. Okay, so if you want to make this set closed, see, if you want to make this set closed, what we have to do? So if we want to make this set closed, so what I can do? I can write this way. So let's say Z contains all those elements belongs to C such that Z contains 0 also, or Z also contains 1 upon n, where n belongs to set of possibilities. Now this is closed. Why it is closed set now? Now because it contains its limit point also. Because the only limit point for this set is 0. Okay. And remember, it contains only one limit point. Okay. What all these points are called as? These points are not limit points. So the elements of the form 1 upon n are not limit points. Why they are not limit points? Because you see, if you mark them, so this would be 1, this would be 1 upon 2 somewhere. अच्छा उल्टा mark कर दिया. This is 1. Let's say this is 1 upon 2. This is 1 upon 4. Then this is 1 upon 3, 1 upon 4, and so on and so forth. So every neighbor, it is not necessary that every neighborhood. So every neighborhood means what? I'll make a small neighborhood about 1 by 2. Now this does not contain the other elements of S. It only contains this 1 upon 2. So what is the condition for a limit point? The condition for limit point is such. What is the condition? The condition is that it should contain, every neighborhood of that particular point must contain
At
points
least
other than Z naught. At least one point other than Z naught. Okay. So if I'm saying that Z naught is a limit point of set S, then every neighborhood of Z naught must contain a point other than Z naught. Okay. Now all these points 1, 1 by 2, 1 by 3 are not limit point, rather they would be called as isolated points. Lately we'll see these points are called as the isolated points. Okay. I've not defined yet isolated points, but these points are called, I'll define it also, but these points are called as the isolated points of set S. Is that clear? So if I'm taking this set S, where set S contains all the complex numbers Z equal to 0 and Z equal to 1 upon n, where n belongs to natural, Z equal to 0 is the limit point. So if you want to define the set of the closed set of the limit points, it is singleton 0. Okay, so this is the set of limit point for this set S. And all these points Z equal to 1 by n are not the limit points, because for limit, in order to qualify as a limit point of a set S, the every neighborhood of that particular set, every neighborhood of that particular element must contain elements other than that particular point. So let's say if I'm saying Z naught is a limit point, then every neighborhood of Z naught must contain points other than Z naught. That's not the case. Let's say if I take 1 upon n naught, and let's say in general I take 1 upon n naught plus 1. So what I can do, I can always, I can always make a distance. Let's say I take this point here. I'll take this point here. Okay. So in general, if I take this distance and this distance, what would be this distance? So let's say this distance is del 1, and let's say this distance is del 2. So del 1 is what? Del 1 is 1 upon n naught minus 1 upon n naught plus 1. And what is del 2? Del 2 is 1 upon n naught. Sorry, this is del 1 and this is del 2. Let's say. Okay. And what is del 2? N naught minus 1 minus 1 upon n naught. So if I select a neighborhood del, which is nothing but half of minimum of del 1 comma del 2, then obviously what will happen? Whatever is the minimum of both, just take a half of it. So this will contain only point 1 upon n. Then del neighborhood of 1 upon n naught will contain only 1 upon n naught. It implies 1 upon n naught cannot be a limit point. Because in order to qualify as a limit point, there must exist some neighborhood. There must exist every neighborhood about 1 upon n naught containing points other than 1 upon n. But I have here defined a neighborhood where you will only find this 1 upon n naught and no other points except 1 upon n. Is that fine?
Yes, sir.
Okay, so I hope it is clear. So now let us move. Connectedness we'll do tomorrow, but at least open and close today we'll do. Okay. And if it is possible, I'll do connected also. Let's see. Connected into calculating. It's no big deal. Okay. Okay. So this is so rather I will say these points 1 upon n. All these points are rather called as isolated points. These are called as the not limit points, rather they're called as the isolated points. I'm not defining them much, but I'm just giving you a little bit of understandings. Okay, so points of S of the type 1 upon n are called as the isolated point. Okay, also remember that each point in the open set, each point in the open set is also a limit point. By the definition itself. Because the definition of limit point is what? A point Z naught is called as a limit point if it contains, if every neighborhood of, if any neighborhood, sorry, if every neighborhood that point contains points other than that particular point. So if a point is interior, the neighborhood would contain points other than Z naught. It is very much in the definition itself. So each point of the open set, each point in the open set is also a limit point. And if you want to define the set of limit point for this open disk, then this will also, the boundary point will also come into the frame. So now let us define boundary of S. So boundary of S is nothing but it is in very simple manner, I will say, it will be the set of all boundary points. The set of all boundary points form something called as boundary. Usually it is denoted by this. Okay, so for example, if I'm considering a set S where set S Z belongs to C such that Z minus 1 mod is less than equal to 1, then remember that Z naught is equal to 1 plus iota is also a boundary point. Because it will be contained in the boundary. You use 1 plus iota here, place 1 plus iota, so 1 minus 1 gets cancelled, iota mod is equal to 1. So equality comes. Equality means you are on the boundary.
Boundary.
Okay. And remember, one of the important things is this Z naught is also is a boundary point, is also boundary pointing, is a boundary point. Why it is a boundary point? Since it is contained where? Uh, since every delta neighborhood of Z naught has a non-empty intersection with both S and S complement. So basically what is boundary? Boundary is something which boundary क्या होती है? देखो generally what we say boundary मतलब मेरे घर की अगर boundary है तो वो मेरे घर की boundary भी है और इधर की भी boundary. So basically for other people it is a boundary that you cannot come inside the home, and for my home it is a boundary that if I cross it I will go outside. So basically I'm making you understand it with very practical example. So if I'm saying something is on boundary, it implies what? It implies what? So if I take any neighborhood, and if I take intersection of this neighborhood with the set S, so if I'm saying that I am considering a point on the boundary, then any neighborhood, uh, let's say I'll define this point Z naught. Any neighborhood of point Z naught, and if I take an intersection with S, this will also come as non-zero or non-empty. And if I take any neighborhood and take an intersection with S complement also, this will also come as, because these elements are there. So basically, if I take the intersection with S or with S complement of any neighborhood of Z naught, then this has to be a non-empty set. So this is how you define your boundary. Is that fine?
Yes, sir.
Okay, so this is how you define boundary. Boundary means, see, what is boundary? Boundary is something which separates. So basically, if you are at home, a boundary would separate you from external surroundings, and external surrounding, this is also boundary because these are homely conditions here. So that way, understand that if Z naught is a boundary point, and if I make any neighborhood about Z naught, and if I take an intersection with inside points, like points inside S, then it has to be non-zero. And if I take an intersection with S complement also, then also it has to be non-zero. Only then I will say that this point Z naught is a boundary. I hope it is clear. Always remember, this boundary is always closed. Okay, so I will write that the boundary is always closed in C. Okay, so basically the boundary points are also the limit points in that sense. Okay, so boundary is always closed in C, and there is something called as closure of set. So what is closure of S? So closure of set S is generally defined as this S bar. And this is defined as what? Is defined as S closure contains what? It contains S union the boundary points. Is that fine? So closure of set S, which is defined as S bar, is nothing but S union the boundary points.
सर बाउंड्री हमेशा क्लोज्ड होती है मतलब
मतलब boundary points are the limit points. In that sense, I'm writing that boundary is always closed in C. Okay, मतलब तुम अगर confused हो रहे हो तो don't write it. Otherwise, what I want to say, let's say, if mod Z, वही वाला पुराना example, if I'm writing that mod Z is less than 1, then the boundary points delta S, that is mod Z equal to 1, will be contained in the uh, will be contained in the will also be the limit point. In that sense, I'm writing. Okay, you can skip this concept. It's not even necessary. If you're not getting it, it's not that way. It's just way of writing things. Understand that boundary points will also are also the limit points. You must understand that particular scenario. Is that fine? No, boundary points are limit points. That is fine.
yes sir
Yes, in that sense, I wrote that it is always closed in C. But most importantly, understand one definition which is called as a closure of set S. The closure of set S is nothing but denoted by S closure, like S bar, and it is containing the points S and also containing the points from the boundary. Is that fine? This is called as closure of S.
yes sir
Okay. An interior point you already know. Interior point is what? A point is said to be an interior point if there exists a neighborhood containing that point contained in that set. So interior point of set S. So let's say if I'm saying that Z naught is an interior point of set S. So how do we define? We define it this way. Okay. So if Z naught is an interior point of set S, interior point of set S, then what? Then there must exist some neighborhood L greater than 0 containing the point Z naught such that it is contained in that set S. Okay. So if there exists some neighborhood of Z naught containing the point Z naught contained in that set S, then we say that the Z naught is called as the interior point, and set of all these interior point is called as an open set. So another definition of open set is that a set is open if and only if all of its points are interior point. Is that fine? I hope
yes
it is
sir
clear till now. No? Now, from tomorrow, like tomorrow, probably we will do something called as connected set. Okay, so that is important. Once we'll do it at a very superficial level, not at a very detailed level. But one has to understand the sense of connectedness, because time and again you are going to see that this is most often used in your most of the things. Like most of the times you'll find that people are defining something called as connectedness and all those things, and without that you will not be able to proceed further. So that is another problem without which you cannot go ahead. Okay. Uh, I may write a little bit of things and then we'll discuss all these things tomorrow. Okay.
Yes,
Okay.
sir.
So let us write connectedness. Connectedness. Let us first, before writing connectedness, let us first write connected set. Okay, and then I'll write more profound definition for connected set, connectedness in the sense of metric space. So a set S, I'm just writing today connected set. You just verify on your own today, and then we'll continue with this topic tomorrow. This is an important topic. A set S, a subset S of complex numbers is called, this is the entire complex field. Okay, is called, what should I write? Is said to be connected. Is said to be disconnected. First, is said to be separated or disconnected. When it is disconnected or separated, if there exist two non-empty disjoint open sets. Disjoint open sets A and B such that S is contained, uh, S is a subset of A union B, and S intersection A is this thing empty, and S intersection B is also empty. This is the definition for not connected. This is the definition for disconnected set. So for defining a disconnected set, there must exist two non-empty disjoint open sets A and B such that S is contained in A union B and S intersection A is a non-empty set and S intersection B is also non-empty. Then we say that this set, subset S of complex numbers, or the subset S of set of complex plane, is a separated or a disconnected set. If this is not the case, if S is not disconnected, then it is called as connected. This we'll discuss tomorrow. So just I'm writing it today so that we'll start from here. It is called as, sorry, it is called as connected set. And more general way of writing this thing would be in the sense of what I can say, metric space. So we say that a metric space X, same definition. Okay? A metric space S X is said to be connected. Is said to be not connected. Sorry, again, the problem is same. Is said to be not connected if there exist two open sets, two non-empty open sets, sorry, two non-empty open sets U and V such that X is equals to U union V and U intersection B is equals to 5. Okay, and we generally say that this U comma V is a disconnection in X. So all these things we are going to start tomorrow. I'm just writing it so that we may lead from here. Okay, so connectedness one has to remember. A set S is said to be disconnected or separated if there exist two non-empty disjoint open sets A and B such that S is contained in is contained in A union B, and S intersection A is also non-empty and S intersection B is also non-empty. Only then we say that the set S is disconnected. And If Z is not disconnected, then we'll see that this is connected. And I'm leaving you with 3 examples, and then we'll see which of them is connected and non-connected. So if A is greater than 0, the set S1 given by Z says that Z minus A modulus is less than equal to A, or Z minus A modulus is, Z plus A modulus is greater than equal to A, not greater than, less than equal to A. Another set S2 is equals to what? It is equals to, let's say, Z minus A modulus is less than equal to A, or modulus of Z plus A is less than A. And the third set S3 is given by all those Z belongs to C, such that Z minus A modulus is less than A, or Z plus A modulus is less than A. You have to see which of these set is connected and disconnected. So we'll see all. हाँ बेटा.
फर्स्ट कनेक्टेड होगा ना.
हाँ जी. So ये तुम कल देखोगे. Tomorrow we are going to see all these things. It is less than equal to, ठीक है ना? It is less than equal, and this is less than equal to. I hope writing is fine. इसमें क्या अच्छी writing बनती नहीं. ठीक है. So we'll see these things tomorrow. So tomorrow's topic would be connectedness, and then we're going to see a few properties of connectedness, path connectedness, and then we'll take it further. So from today itself, you can understand that we have started something called as complex analysis. Okay, and all these definitions are going to come again and again. So don't worry. Right now, just keep them in mind. Again and again, you will find that I'm going to use something called as open set, closed set, because here the domain means open and connected set. So whenever I'm saying domain, it implies what? It implies open and connected set. So the point is that every time I'm going to write domain, every time you have to associate it with open and connected set. So here domain of definition means the way we used to write in the function. Let's say 1 upon x, the domain is x not equal to 0. Here domain set is a topological term, which means it is both open as well as connected set. Is called as a domain set. So that's why I'm doing all this business. Otherwise, you will get confused while studying these things independently from books, because probably books will not define all these things in greater detail. They will directly start with things. So that is why. Although Indian author books will not do so. Indian authored book will have a introductory part. So Indian authored book will not have a problem. But if you directly are going to read Rudin, okay, so I don't think Rudin is going to explain all these things in greater detail. He's going to write directly the things. He's going to assume that you already know something called as open set and closed set and all those things. So, and metric space. So he'll directly use the terminologies. Okay, so that's why I'm doing all these things. I hope it is clear till now. Okay.
Yes, sir.
Okay, so we'll meet tomorrow. Till then, take care.